Okay. Well, thanks very much indeed for the invitation to join you today. Let me just share my screen here. Hopefully you can see that and I can put that on display. Is that okay?
Works great.
Okay, fantastic. So as you will have heard from the introduction there, and you'll see from the title, this talk is going to be about infrastructure systems and their vulnerability to a changing climate. That's also, as you heard from the introduction, not the only thing I work on, but it's what actually is consuming the majority of my time at the moment. I think as we've had the IPCC Working Group 2 report last month, and really rapidly growing awareness at the Glasgow Climate Conference, and looking ahead to Sharm el-Sheikh next year, and a whole series of initiatives around adaptation, that this agenda of infrastructure, its vulnerability to a changing climate, and the way in which it is a focal point for adaptation is going rapidly up the agenda. We're working amongst other places, I mean, doing research in many parts of the world, and as I'm saying, I will explain, developing network analytical capabilities, the goal of which is to apply them everywhere on Earth, as I'll also say, doing that is not necessarily at all easy for a number of reasons. But one place we're currently working in collecting data and analyzing is the infrastructure networks in Jamaica, which is where this image comes from. And it's actually at Glasgow in December. I heard this remarkable fact, in fact, that the Caribbean contains less than 0.5% of the world's population, but it is subject to about 30% of the world's natural disaster loss and damages. And so if you're being hit by extreme natural catastrophes year after year, which are impacting infrastructure systems, people's homes, the economy, supply chains and businesses, then that is a real impediment to development. It can, and we've done some simulation modeling of this with stylized economic models, it can land you in a poverty trap, whereby successive and possibly increasingly severe disasters really shift in a non-marginal way, in a structural way, what a country's development pathway looks like. And so if one is in a country, and this doesn't just relate to low and middle income countries in the most vulnerable parts of the world, it relates to all of the countries that we live in, I think. If one is facing the threats of recognize that the information that is at most decision makers' disposal in terms of what are the critical infrastructures, what are the climate hazards to which they're exposed, how severe those hazards are, what level of economic disruption might occur, how long it might take to recover, what finance is needed to recover, how risk might change in the future, and indeed what are the options for responding, and how should one create adaptation strategies for responding. All of those questions are very difficult questions, and in most instances there are not very robust answers to them. That was certainly the case in the UK, where, as was mentioned in the introduction, I sat on the Committee on Climate Change, the government's advisors on climate change. We conduct a climate change risk assessment once every 5 years. And the answers to the types of questions which are written here are still frustratingly incomplete. So these are the types of questions which we are trying to work on in research terms in order to better inform adaptation decision making. And the call for that, I put this one here. This is very recent, just from less than a month ago, from the Association of Small Island States, a call to the international community. And I've included this this slide below, the quote below, which refers to small island states called for physical climate risk assessment tools, which will help small islands to understand the climate risk to which they're exposed. That just struck me as being yet another call for to fill these gaps in terms of climate risk to infrastructure systems. And of course, the audience I'm speaking to now is in New York City, which is well known not only for the impacts of Hurricane Sandy, but also for the work which has been done since then on adaptation planning. Just to give a kind of cut to the chase, cut to some of the answers to these questions. This is a snapshot from a prototype tool which my group developed for the World Bank last year, which provides the type of geospatial information here, looking at power grids, railways, trunk roads, across most of Southeast Asia, and doing with a large event set of both flood data and hurricane data, cyclone data, probabilistic risk analysis of the probability of failure of every road in that network, every power line in that network, estimating what the expected damages might be, what the economic losses might be, and using that to target hotspots of vulnerability and priorities for adaptation decision making. I'll come back to this right at the end, but it's useful to kind of get a picture in your head in terms of what a version of the answer looks like before we talk about some of the sometimes gory details of how one actually goes about creating an answer like that. And the framework which we work to looks a bit like this, with starting with some hazard footprint. We don't, though I've worked on flood modeling quite a bit in the past, both the fluvial and coastal floods. Right now, we're getting the hazard data from elsewhere, and our focus is on the exposure of infrastructure networks and the processes that are being enacted on those networks, the power flow, the traffic, and the water flow, the data flow in telecommunications networks, how those flows can be disrupted, the possibility for cascading or interdependent failures, and then what are the economic impacts of those types of disruptions, using that to calculate risks, intervening in the system with adaptation options, recalculating risks, what's the residual risk, estimating the benefits of adaptation and comparing that with the costs. But there are some quite technically difficult aspects of that problem, which I will say some words about very briefly in this presentation. And anyone who's worked on this kind of problem, and I guess there are some people here today who are will recognize those words and understand why they're difficult. I'll just say, I won't go through them now because I'm going to go through each one rather quickly, one by one. And underpinning all of this is the fact that we don't have as much data as we would like to. There's a lot of kind of ingenuity involved in coming up with answers in situations of very scarce data. But ingenious as we may be, and as creative as we are with new data sources, the abundance of things that are coming through satellite Earth observation, crowdsourcing, and so on, we're still facing very significant data gaps. But let me just skip through some of these tricky problems. And I think a really technically interesting one, but still tricky, is the fact that the hazards to which our networks are exposed are more or less spatially coherent. Here are 3 floods from Britain to illustrate the point I'm making, that if you're calculating the probability of failure of maybe Britain's rail network, you need to recognize that the network is not being hit by independent events. The events have a clear spatial coherence to them, but every event is different. So we need to understand the statistics of these spatial events. There are some good statistical methods for this now, including copular-based methods, or in some instances, we're using the outputs from weather and climate reanalysis data or model data or observed data, which implicitly contains that spatial and indeed cross correlation between variables. So quite a bit of what will follow is based on very large model-based ensembles of synthetic weather, which we're using in risk analysis. But this is a really nice illustration of why this spatial dependence problem matters, is the question of what's the probability of at least one river gauge across an area like the size of Britain having a 1 in whatever year return period event in any given year. Let's focus on the 1 in 100 year return period event. If each of those gauges, and there are 900 odd gauges across which we use in this analysis, if each of those gauges were independent, then you would see a 1 in 100 year event almost for sure every year. If they were fully dependent, then obviously the probability of observing a 1 in 100 year event would be 1 in 100, so 0.01. In fact, if you do the statistics carefully, you come up with a result which certainly surprises politicians who ask the question, well, why are these 1 in 100 year events coming along so often? Is that across Britain, the probability in any given year of having a 1 in 100 year event is about 0.75. So it's certainly more likely than not that you're going to observe a 1 in 100 year event somewhere in Britain in any given year. That's the type of contextual information which helps to explain some of the things one sometimes sees in the press, and is also fundamental to then going on to analyzing extreme events. Here's an example of doing this analysis with climate model outputs. These are lots of synthetic droughts, which were used to stress test the water supply system. I'll skip over that. So that's the first kind of problem we face, is properly characterizing the statistics of extreme events. The next problem we face is, and engineers will like this, is properly characterizing the physical response of infrastructure assets when they're subject to extreme loads. Here's a foundation, not a very good foundation, of a masonry arch bridge, a railway bridge, which has been subject to a very extreme river flow, an extreme flood down a river, which has scoured away around the foundation, and it's a surprise that this bridge is still standing at all. So this, in technical terms, we think of as being a problem of structural fragility. What's the conditional probability of failure of the bridge given the load? We've done some quite a bit of work on this problem. I won't go too much into the ins and outs of this. I'm conscious of time, but we did we had the benefit of having actually quite a large number of observations of bridge failures, which go back a long way in time. By some coincidence, exactly 100 bridge failures have been observed since 1846. And we're able to reconstruct most of the floods which occurred and led to those bridge failures. So by doing some statistics, which will be of interest to at least some of you, we're able to look at both estimating from the observations, what's the probability of bridge failure for a given flow in the river, but also we can use the observations of the non-failures. So the fact that a lot of bridges have survived extreme flows and they're still there, to modify our statistics in a Bayesian sense and come up with a much better estimate of this fragility, the conditional probability of bridge failure. And so the large-scale climate risk analysis problem involves generating lots of curves like this for lots of different types of infrastructure assets, and entering that into our network risk analysis. The next thing I'd just like to say a few words about is the fact that infrastructure networks, not only are they complex in their own right, but they're also interdependent on one another. Practically everything depends upon electric power networks these days. Practically everything actually depends on some versions of telecommunications. And so we've spent a lot of effort in order to understand the possibilities of not only cascading failure within networks, but also interdependent failures across networks, characterizing exactly how these networks are hooked together across Britain. And that, because of the dependence on electricity, we start by building a very complete model of the electricity network, quite a complete model of the telecoms network, road, rail, water, and hooking all of that together as best we can based on admittedly only partial information, but and quite a lot of engineering judgment in terms of how those networks are hooked together. And what that can enable us to do is to identify the critical assets within the network, which, were they to fail, lead to the greatest number of user or customer disruptions, not only due to the failure of the asset itself, but also due to the interdependencies which might flow from the failure of that asset. And these diagrams here illustrate some of the scale of those interdependencies. So here we start on the left with electricity failures. In this simulation, we tested just over 18,000 different failures within the electricity network. And 40% of those then led to failures within the telecommunications network. Quite a lot of them, well, some of them led to failures across the water and the rail networks as well. And the interesting thing then is from that 40% which led to telecoms failures, another 20% then led back into the electricity network to cause more failures. And you can see from this diagram how the whole failure sequence propagates through those interdependencies. And this was for the National Infrastructure Commission. And one of the questions we had was, well, if one were to be able to add more interconnectivity, more redundancy, and indeed more backups into the network, how much benefit that would have. And you can see that if it was possible to add another layer of redundancy, then that propagation of interdependent failures would be much reduced. The next thing I just want to say a few words about is, once failure has occurred, how does that impact the economy, supply chains, for example. So when failure occurs, when a power network failure occurs, which is what we're simulating on the left here, then that leads to businesses not operating, in not producing. If they don't have any power, they can't supply to the people who are expecting them to be supplied to. So downstream in the supply chain. But they're also, they cease to demand to be able to accept goods and services from upstream in the supply chain. There are also impacts in that their workers, if they're hit by the failure as well, their workers can't travel to work. They may be paying attention to vulnerable members of their family, have caring responsibilities, and so on and so on. So there's a whole series of different layers through labor markets, on the demand side, on the supply side, in terms of how the infrastructure failure may propagate through the economy. And we've done quite a bit of work with input-output models, looking at simulating these effects. The pictures on the left are using a regional economic input-output model to give some sense of the economic loss per day. And in looking at that, this is analysis for the UK Environment Agency. We found that the disruption from the potential disruption from flooding of infrastructure assets in the floodplain is much, much greater. 8 times as many people and properties are potentially at risk from loss of infrastructure services during floods than are at risk from flooding itself. Now, the nature of the harm which they incur is rather different. Having your house flooded is different to being rendered without power or without water, but nonetheless, that potential for very large-scale disruption is often overlooked. For example, in cost-benefit analyses of flood protection. And we were able to quantify some of those wider economic impacts, and indeed then the benefits of more resilient flood protection for infrastructure systems. We did a version of this actually for the World Bank, looking at flooding in Vietnam and how severe floods in Vietnam might impact economically, again, through supply chain interconnections, into enabling countries in a very significant way. And a quite recent part of our work has looked very specifically at ports, looking at around 1,400 different ports worldwide, and the effect that port failure can have both on imports on the left and exports on the right, and the economic losses which might occur due to port failure. And one instance of this, which we looked at with the Hurricane Ida disruptions to grain exports from Gulf ports in the USA, and how that propagates around the world to grain importers in a great diversity of countries. So that was all about risk analysis. The question, and risk analysis is important and interesting in its own right, but what really matters is what do we do about it? How can we use this type of information to enhance resilience? And by enhancing resilience, we think about the capacity of systems to resist or absorb shocks. So in engineering terms, you might simply think about this as making systems, assets stronger. But then resilience, as we know, is wider than this. It relates to the capacity to cope during shocks, to recover, so to get systems back up and running as quickly as possible, and also to learn from failure and enhance systems to build back better, if you like, following a shock. So within many of these risk analyses, we've looked at ways of intervening in systems in order to make them physically more resilient to climate-related threats. And we've looked at the costs of these interventions. The World Bank has done a bit of work on this, but costing data is actually rather hard to come by, and we could do with a lot more of that. What you might spot from these numbers is that these interventions are not cheap. This was in Argentina. We're looking at millions of dollars per kilometer and very significant increases in the cost in order to be able to cope with climate change. I'll come back to this in a moment, but I've seen a few things recently which somehow suggest that adapting infrastructure systems to climate change is a no-brainer. I think it certainly is when you're designing and planning those systems. But if you're thinking about retrofitting them, retrofit can be extraordinarily costly, and we have to make some really difficult decisions in terms of where and when do we decide to retrofit before assets arrive at the end of their lives and would need to be rehabilitated or replaced anyway. And in those types of decisions, we need to consider not only, and this is below the line, the initial investment cost, but also the maintenance costs. And those are weighed up again, as I said at the start, against the benefits of risk reduction, so the benefits of avoided damages. And typically we expect damages to go up into the future. We're expecting more people, more economic activity, and quite possibly more severe climate extremes. So by the same token, the benefit of damage avoided is likely to go up for any given adaptation option as we go into the future as well, which is what's depicted in this picture. So the discounted benefits on the top and costs on the bottom need to be compared with one another. We did a version of this calculation again for the World Bank for every road in Vietnam. And you can see this, the different flooding scenarios that were looked at. The interesting thing here is the picture on the right, which is a little bit small, but hopefully you can see that the y-axis of that graph there is a log scale of benefit cost ratio. So on that scale, 10 to the naught is 1. So this, everything below that red line is actually not cost beneficial to do. That indicates that there are many different ways of wasting adaptation money on the transport network in Vietnam. What it also shows you, though, is that there are, if you look at the right-hand end of that curve, there are a lot of things which are above 1. So if you're able to prioritize, then there are some things you really should be doing in order to enhance the resilience of this transport network. We did quite a bit of sensitivity analysis around that. And these pictures illustrate that sensitivity analysis. One aspect of sensitivity is how much economic activity will go up in the future, GDP growth, which is on the left-hand side of these pictures. The more GDP growth there is, the more benefit there is to avoid losses. And then the x-axis of these graphs, the other key bit of sensitivity is how long do we assume that delays will go on for when a disaster occurs? How quickly can you repair? And that's absolutely critical because by first approximation, the amount of loss is a linear function of the number of days of disruption. And so what we're looking at on these graphs is how many kilometers of road on the top, and on the bottom, how many bridges is it worth replacing subject to those two sensitivity parameters. I hope that makes sense. So I've gone through a few hopefully interesting aspects of doing the type of analysis I've illustrated here. Just to before I close off, I'll say a bit more about how we're the main part of our research program now is to upscale this type of analysis. I've mentioned some of the data products which are now available, which enable one to do this type of analysis everywhere on Earth. So for the road network, the crowdsourced OpenStreetMap data set is an incredible resource. It's certainly not perfect, but it's amazing nonetheless. There are a number of different global climate extreme products. So that has enabled us to do this analysis on the right a couple of years ago now, with the World Bank, which was the first global multi-hazard analysis of road and rail infrastructure assets. So this was around 60 million kilometers of road and rail assets doing the type of analysis I've described. And then in terms of infrastructure data sets, as I say, there's a bunch of things becoming rapidly available. This is an image from a tool called Grid Finder, which some people in my group work with the World Bank on to create real and synthetic power networks everywhere on Earth again, and we're combining that with a global tropical cyclone data set to do a power network risk analysis at the moment, with a large synthetic event set to look at the risk of power network failure in the tropical cyclone zone everywhere on Earth. Which brings us back to this this image that I started with, which kind of illustrates where that then all leads in terms of this capability to provide tools for risk analysis and adaptation options appraisal for decision makers at very large scales. This provides some of the other ways in which the results can be presented. So these are at subnational levels, admin 1 or admin, mostly admin 1 level, maps of expected annual losses. And then the inset graph on the right shows loss probability functions. You can click on the graph and look at the loss probability curve in order to provide this very high resolution picture of what climate risk is now and how it might evolve going into the future. We presented some of this at COP26 as part of an initiative called the Global Resilience Index Initiative, which is an initiative to try to create comparable risk-based indices of extreme climate risk, the kind of common language of risk everywhere on Earth, which is where we're trying to get to. Quantified spatial analysis of climate risk to infrastructure everywhere, then using that to estimate economic losses, attribution of those risks to within the networks, because that really enables prioritization of resilience planning, engineering design, asset management, finance, and doing this in an open and accessible way, so that we can build capacity amongst decision makers and enable participation in this type of decision making. And I will finish there, and I'd be very happy to answer any questions that you may have for a few minutes.
Thank you, Professor Hall. Thank you for delivering so succinctly the major climate change adaptation challenges across resilience timescales and different infrastructure systems. Let's give a warm round of applause to our speaker. Okay, so the Q&A is now open. Feel free to raise your hand. I see there is one question in the chat. So feel free to either type your question in the chat or raise your hand, or just unmute yourself and ask. So Charlie Midlars asks, how has the process of collecting urban infrastructure data been? Is it an uphill struggle to have these stakeholders share the data that you need? And that was in respect to the first part of the presentation, when there were the different infrastructures and the coupling and the understanding of the cascading effects.
So the short answer is yes. Let me expand on some of that, particularly in the urban context, which I know is a particular interest of this group here. I mean, some particular challenges in urban areas relates to underground infrastructure, and there's one example of that relates to stormwater infrastructure. There's lots of interest in terms of stormwater flooding, the potential of increasingly intense rainfall downpours, and how that can damage and disrupt urban areas. And it can be vastly expensive problem to deal with, or one might wish to integrate sustainable urban drainage systems, but that represents a really kind of challenging and long-term land use planning and design challenges. So understanding exactly what the urban drainage infrastructure is and what its capacity is just one example of how difficult urban infrastructure is to obtain information on. The other kind of data difficulty which I would point to, which you'll have kind of got implied from what I was talking about, is validation data in relation to the actual infrastructure performance during disasters, so that we can validate these simulation models that we're constructing.
That's thank you so much. That's really, and just thank you for your talk as well. It's really interesting. And yeah, you kind of exactly nailed what I was getting at. Like I was considering the MTA, for example, who run the subway system in New York. Like they have huge amounts of assets underground that are, yeah, particularly at risk of flooding scenarios. But also there's a reluctance to share too much information about this critical infrastructure because of security concerns. So we have that pushback from the city. They can't tell us everything because, you know, you can't make public the locations of all these critical assets, but it's important for us to understand what's under there and how it's going to be impacted by flooding in particular. But yeah, yeah, thank you though, that really helps.
You know, this is Yuri from Rochdale. Hey up, Jim. It seems like it's all Brits on this bloody call. Anyway, the question is, just to follow up from Charles' question, which is, how can you provide this kind of data and protect it from disruption by certain Eastern European nations?
So one part of this, just kind of speaking from my own experience, is that one has to be really patient, get to know the stakeholders who you're working with, kind of enable them to get to know you, and also to focus on the problems that they're confronting so that they can see how you might be able to help. Another kind of angle on this, it was mentioned in the introduction that I'm chair of a piece of national compute infrastructure called the Data and Analytics Facility for National Infrastructure, DAFNI, which is basically a kind of compute system at one of our national laboratories, the Rutherford Appleton Laboratory at Harwell. And DAFNI obviously has lots of hardware rapidly going out of date. That's the problem with big compute investment. But it has a software platform, a rather nice kind of workflow analysis set up, which enables you to couple data sets with multiple simulation models and visualizations. And that's useful for stakeholders because they have the security of this system being at a national laboratory rather than a university, which is always being hacked by Eastern Europeans. So they kind of trust the security. They also, because of the workflow set up on DAFNI, they can use these models themselves much more readily. You press a button on a workflow and it executes the model and recreates the graph. So that's kind of useful. And so the Environment Agency, for example, is using our water resource system model of England on DAFNI, because also, actually, by the way, because they can't install this model on their own systems because their own systems are so closed down by their IT team. that they can't install a complex simulation model on it. So Daphne solves a problem for them in that sense. And then also most recently, we've had a project called Credo running on Daphne, which had both the Eastern Power Utility in the east of England and Anglian Water sharing data with each other in a way that they hadn't previously been willing to do, because it was being shared within the secure Daphne environment. So they didn't actually have to kind of give data to each other. The model was coupled on Daphne using the two different data sets from the two different utilities, but whilst keeping that secure. So that's a kind of interesting techie example of how one can possibly circumvent some of these security issues.
Thanks.
Are they also sharing the condition data on these assets that they're operating? Like in the case of the water companies and the electric companies, are they sharing like critical asset conditions, like ages of motors and any kind of like points of failure, or are they holding that stuff back?
Yeah, the ages, so the asset database is part of the Credo project. As you're suggesting, there are plenty of good reasons why they don't want to share all of that, not just because of security, but also because they're, to be completely honest, well, how can I say this generously? Well, no, let me say it ungenerously. Sometimes they're trying to game the regulator. There's an element of the information asymmetry with regulators is partially to their commercial advantage.
Thank you.
Thank you.
We have another two questions in the chat. First one is by JP McKay. Do you have any opinion on the value of increasing grid interactive distributed energy resources in regard to their attributions to resilience compared to resilience attributable to redundancy in an electric system?
Yeah, that's a really good question, and the answer is it depends. Instinctively we would expect a system which is more distributed and with more storage on it to be more resilient. But then we know that those renewable supplies are intermittent, and so that kind of acts in the other direction. Also, if you're looking at photovoltaics in particular, which depend upon inverters, then they don't bring any inertia to the grid. So there are issues of grid stability if you end up with very large proportions of photovoltaics and you don't have enough high inertia power supplies from other sources. I think, and one kind of general thing, and it's probably quite an obvious thing that can be said though, is that on the whole, in particular in advanced economies like in North America and in Europe, we're bringing renewables onto already highly integrated transmission grids. So the existence of a legacy transmission grid is really crucial in terms of providing resilience to a network which ends up with a lot of distributed renewables and storage on it as well.
Thank you, Professor Hall. And yeah, just my 2 cents, the problem of inertia is really coming up when you take out all of those large generators, but then you need storage. How do we do that? Really interesting engineering problem. Second question by Chris Novel. Thank you, Professor Hall. The question is, does the data gathering and analysis include any, I guess, data about animal and insect impact?
So the short answer to that one is no. I'd like to understand actually a bit more about what instances where those things you've referred to, animal and insect impact, have been associated with disastrous infrastructure failures. So let me turn that around. I want to know more.
Feel free to ask Chris.
Hi. What I know is that anytime a road, for instance, is put in anywhere, it can disrupt what was the natural pathing or habitat of those creatures. And so then when there's a damage to the initial road, or whatever other structures, it would seem that that could further impact on those creatures. And so to understand how that can affect the viability of those locations, that's the thought that I have.
Okay, so that's really interesting, and I have to say that I'm afraid we haven't looked at that. We do. I look quite carefully at the interplay between infrastructure and nature. We had some work going on looking at how nature recovery networks or corridors can be planned at the same time as, or indeed in anticipation of infrastructure developments. And I think that's, if one's looking at places where large amounts of new infrastructure are anticipated in the future, in particular in Africa, then incorporating nature corridors in advance of that infrastructure development is rather crucial for biodiversity. So that is something we're looking at, but the precise problem you've just asked is not something I thought much about. I will do.
Thank you, Professor Hall. Thank you for the question.
Thank you.
I see we have 2 more minutes, and we have one last question on the chat. Do you include the impact of potential net zero actions and future infrastructure demand in regional loss models by Neil Ferguson?
Yeah, so this question around the resilience of the transition to net zero is a really interesting and an absolutely crucial one. So it relates to what we were talking about previously about for example, about the resilience of renewable energy networks. And so how do we plan a resilient transition to net zero would be one way of talking about that. And aspects of that we have looked at, including on the demand side, which is mentioned in the question. So we've looked at the resilience of the power network in the context of much higher degrees of electrification of heat and transport. So parts of this question we've looked at, but it's a great question, and there's a lot more to do on it.
And 30 seconds, contribution by Juan Bello. A thought on Chris's question: how about, for example, incidents of insect and waterborne illness as a function of flooding, or an incidence on health infrastructure? I guess these are all potential venues, from what I understand.
Yeah, and I mean, clearly infrastructure and water infrastructure in particular is an essential aspect of public health. And as is implied in Juan's question there, when we have disasters, then the health implications of those disasters are a very big part of what people worry about. I kind of have to admit that the specifics of health impacts, well, let me put it another way, that we, as well as looking at economic impacts, we also, and some of the results you've seen there, quantify impacts on people. And in that impacts on people, we've also done quite a lot of work on the distributional effects. So in particular, what the impacts are, whether the disproportionate impacts on poor people, that's still at the level of counting the number of people or poor people who are impacted without actually going into the nature of the harm which they incur, which is what is implied in that question there. So lots more to do in that space as well.
Thank you, Professor Hall. The chat is really blasting. This is thank you everyone for your questions. We are right at the mark, so we will end here. Thank you again, Professor Hall, for joining us today. Let's give a warm round of applause for this seminar. We will not convene next Friday. We will convene the Friday after, and that seminar will host Dr. Juliana Freire from our very own Vida Lab. Thank you again, Professor Hall, and thank you everyone for joining today. Have a great weekend.
My pleasure. Nice to meet you all.
Thank you.
Bye-bye.
Bye.